Okay, so we've been talking a little bit about chemical equilibrium. So I thought this would be a good time to do a couple of practice problems together. So here's one practice SAT problem that you might see having to do with chemical equilibrium. 3 moles of diatomic hydrogen as a gas and 3 moles of I2 as a gas are introduced into a 1 liter box at a temperature of 490 degrees Celsius. Find the concentration of each substance in the box when equilibrium is established. The equilibrium constant, which again here is listed as Keq, right, is equal to 45.9. Okay, so let's just take a moment to parse what that means. We already know from the previous videos that the equilibrium constant, right, for any given generic equation, A plus B is in equilibrium with C and D, gives us this equation, right? C and D over A and B. So in this case, right, essentially what that would mean is that our equilibrium constant, Keq, is equal to, well, actually, let me back up. Let's start by coming up with the actual chemical equation here. We know we've got H2 and I2. And we know that not necessarily all, but when you put them together, some of those are going to become, they're going to get smushed together and become HI molecules, right? Okay, so looking at this from an equilibrium constant perspective, right, essentially what that would mean is that you've got some amount of HI to the power of its coefficient, which in this case is 2, over some amount of H2, and its coefficient is just 1, so it's not going to have a power. And then I2, which again has no coefficient, so it's just going to be to the 1 power, right? So, and we know that that's all equal to 45.9. Okay, I'm going to put a big old circle around that. Okay. So now let's think a little bit about proportion. We know that we started out with 3 moles of H and 3 moles of I, right? And then we've got some unknown number of moles of HI, which are going to come from taking away from some of the moles, some of the 3 mole of H and some of the 3 mole of I. Right? So to start out with, at least, when we start out, we have 3 mole of this, 3 mole of this, and 0 mole of this guy. But that's going to change, right? Because in order to have these in balance and equilibrium, we got to have at least something over on this side, right? So let's say that, again, we know that we're always going to have 1 H and 1 I taking away, right, from over here. Essentially, H2 is going to give up an H, I2 is going to give up an I. They're going to go play nicely with each other over here on the other side of the equation, right? So we know that this will always be in balance, right? So for instance, if I thought of the equilibrium here being 3 mole minus X for H, right, where X is the number of moles of H2 that are going to form HI in equilibrium, right? Then I could say the same exact thing about I, right? Because I'm going to need that those two x's have to be proportional to each other if I don't want like lopsided HI molecules, right? So this is going to become 3 mole minus x, this is going to become 3 mole minus x, and this is going to become, you guess it, 2x, right? So now I can plug that information back into my original equation. Let's do that. So Keq equals 2x squared over essentially 3 mole minus x times 3 mole minus x equals 45.9. And you guys may have noticed that this could essentially be rewritten. This bit could be rewritten as 3 minus x squared, right? Essentially what that means, right, is if I wanted to simplify here, I could just put a square root right over everything, right? Let me just write out what that would look like. So square root of 2x squared and 3 minus x squared equals square root of 45.9, right? And that would just get rid of all my exponents and leave me with 2x minus 3, over 3 minus x equals square root of 45.9, which I will just tell you I found with my calculator earlier to be about 6.77, right? And then from there, it's just a matter of solving for x, right? So when I solve for x, I find that x equals 2.32. So there's an example of how you might solve an SAT chemical equilibrium problem. The final piece here, of course, is actually answering, the original question, haha, right? Which is essentially, what is the concentration of each substance? So now that we have found X, essentially all we have to do is plug that back into these original values. So for instance, H2, I said, was going to be 3 mole minus X, right? Well, now I know X is 2.32. So in other words, I know that that ended up being 0.68 moles per liter, right? Same goes for I2. Because remember, that was just the same thing. So 0.68 moles per liter. And then for HI, that was just 2x, which ended up being 4.64 moles per liter. Excellent. Okay, and one more equilibrium constant problem before we move on. Because again, I know these can be tricky. It's always best to be double secret sure we understand it. So here is a practice problem, and again, just a heads up, this is actually an MCAT practice problem. So when the reaction 2A plus B reaches equilibrium with 2C, and they tell you that you have a concentration of A, 0.1 molar, where again, molar, remember, just refers to moles per liter. So 0.1 concentration of A per liter, and C equals 0.2 molar. And they tell you the value for the equilibrium constant here is 8. They want to know what is B at equilibrium. Okay, well again, first thing to do here probably is just set up our equation. We know that the equilibrium constant is going to be equal to the concentration of C raised to the power of its coefficient, in this case 2, over the concentration of A raised to the power of its coefficient, which is also 2, times B, concentration of B, raised to its coefficient, which in this case is just 1, right? And we know that all of that is equal to 8 because they tell us so. So now we can go back in and plug in our values, which we already have for A and C, and solve for B. Okay, so here we go. We got equilibrium constant equals, okay, we know that C is a concentration of 0.2 molar squared. Okay, A we can plug in as being 0.1, and that's also going to be squared, and that's times B, and that all we have said equals 8. Okay, so time to do a little math, right? That's what I'm thinking. Okay, so this would be a good time to get out your calculator if you have it. And we will take a look at the results together. Okay, you got it? You know, if you could do it without your calculator, cool. But, you know. So 0.2 to the second power divided by 0.1 to the second power, you can think of as being essentially the equivalent, actually, of 2 squared over 1 squared. And again, this is all times B, right? So that's essentially the same as saying 4 over B equals 8, right? Which we can do a little sort of some quick rearranging here, and we will quickly realize that means B has to be 1/2 or 0.5 molar. 0.5 molar, which would mean that our answer is D. Woohoo! And again, if you can do this for an MCAT level problem, trust me, you are going to be just fine on the SAT. All right, I think this does it for chemical equilibrium problems, or at least equilibrium constant problems. Probably we should move on now to Le Chatelier's principle.